In this lesson, we are going to talk about solving and performing operations with complex numbers. So when we are solving quadratic equations, there are two methods that we have already talked about. We've talked about factoring, and we've also talked about square root, factoring, and the square root property. Okay. And sometimes when we solve these equations, we get a x squared equals a negative number, and we couldn't solve it at that point because if you think about it, any number times itself will be positive. Negative 3 squared is positive 9. So if we have a situation where we said x squared equals a negative number, what number times itself equals negative 9? Well, up to this point, there hasn't been a number. So that is what we're going to talk about today. Before we do that, let's look and see what appropriate strategy would we use to solve these quadratic equations. So this one, 2x squared plus 11x equals negative 15. Because I see that we have an x squared and an x term, that is going to be a clue for me to factor. And when we solve by factoring, we want to get the equation equal to 0. So this is going to be 2x squared plus 11x plus 15. Now that this equation equals 0, we can solve by factoring. I notice that my c term is not a perfect square, so that means we can't use a perfect square trinomial shortcut, and we can't think about difference of two squares. So that means I'm going to factor this by grouping because my a value here is 2. So I'm going to multiply 2 and 15, and that gives me 30. And I want two numbers that multiply to 30 but add to 11. Those two numbers are going to be positive 6 and positive 5. And we have 2x squared plus 6x plus 5x plus 15 equals 0. And then we factor by grouping 2x, and then we get x plus 3. And here we factor out a 5, and we get x plus 3 equals 0. So our two factors are going to be x plus 3 and 2x plus 5 equals 0. X equals negative 3. And then for this one, that's going to require a little bit more work. So 2x plus 5 equals 0. 2x equals negative 5. X equals negative 5 over 2. X equals negative 5 over 2. So that will be our solution. And that is the most appropriate or the most efficient way to solve this problem. Over here with letter B, when we have vertex form, and this is vertex form because we have parentheses squared, the most efficient way to do this is using the square root property. So we can divide both sides by 2. And we get x minus 8 squared equals 44. And when we square root both sides, we get x minus 8 equals plus or minus the square root of 44. And what I will do first is break this radical up. X minus 8 equals plus or minus. 44 is going to be 4 times 11. The square root of 4 is 2. So 2 times the square root of 11. Then I have my two equations. X minus 8 equals negative 2 square root of 11. and x minus 8 equals positive 2 times the square root of 11. And then when we add 8 to both sides, x equals 8 minus 2 square root of 11. X equals 8 plus 2 times the square root of 11. So those would be our two solutions. And again, it was more efficient to do it this way because we have this x minus 8 in parentheses squared. Now, letter C, one of the first things you might notice is that both of these numbers are even. And this is one of those questions where there's a couple ways that you could solve this that are almost equally efficient. You could subtract 2 from both sides and then factor out a 2, and you would get a difference of 2 squares and do that. But that seems a little bit more work than just dividing both sides by 18. When we divide both sides by 18, we get x squared equals 2 over 18. X squared equals 1 over 9. Okay, now we can square root both sides. We're going to get x equals plus or minus. The square root of 1 is 1, and the square root of 9 is 3. And we have our answer there. So in this instance, factoring may have looked like it was going to be quick, and it probably would have been quick, but this was even faster to do it this way. Now, if we had to rationalize the denominator, if this 9 down here wasn't a perfect square, then maybe you could talk about factoring, and that may have been a better solution than this. So, like I've said before, I'm giving you tools to use, and then you have to determine which tools to use based on the information given. The beautiful thing is that all of the methods work. You could factor, you could multiply this out and factor that, and you'd still get the same answer. It would take a lot of work, but you could still do it. I want you guys to be able to recognize the most efficient way to solve these problems. So going back to what I was saying earlier, now what we can do is we can worry about what happens when we get a negative number in our square root. What we can do is we can replace that with I, the imaginary unit called I. And when we do that, it's like factoring out a negative 1, and that will make life easier for us. And it's also important to note that if I equals the square root of negative 1, if I square both sides, the square and square root go away, you're going to get I squared equals negative 1. So if we ever have a situation where we have I squared, we can replace that with negative 1. So let's solve this quadratic here. I notice that I do not have a b term. I don't have an x to the first power. So that tells me that I want to solve this by square roots. If we subtract 18 from both sides, we will get 2x equals negative 90. We'll divide both sides by 2. We get x equals negative 45. Sorry, x squared. X squared. When we square root both sides, we're going to get x equals plus or minus the square root of negative 45. Now, at this point, depending on who you're talking to, they'll say, you should do x equals plus or minus square root of 45 times the square root of negative 1, and then change it to I, and I understand that. To me, as soon as you have the square root of a negative number, just know that you're going to have the imaginary unit, or I, in your answer. You may not necessarily need to do this step right here. Now we need to simplify the square root of 45. So x equals plus or minus. The square root of 45 can be written as 9 times the square root of 5. Remember, we still have the square root of negative 1, but that's going to be I. I'm making that change now. So then x equals plus or minus. The square root of 9 is 3. And then the square root of 5 still stays there. And then our I just gets tacked on at the end. So this would be our final simplified answer to this quadratic. I want you to notice, though, that the square root bar does not go over the I. If you do that, that is incorrect. Your square root bar cannot go over the imaginary unit because we've used it up. Look at right here, becomes just I, outside of the square root bar. So please be mindful of that. It's very easy to get careless and just make your square root bar like that, and you would lose points for that because you're giving me an incorrect answer. Over here, we will subtract 3 from both sides. Sorry, 33 from both sides, and you get 5x squared equals negative 30. Divide both sides by 5. X squared equals negative 6. When we square root both sides, we get x equals plus or minus the square root of negative 6. And from this point, I'm just going to go x equals plus or minus the square root of 6i. Because I know that we're going to have the square root of negative 1 here. So this would be our answer. Now we're going to talk about something called complex numbers. A complex number is written in the form a plus b times I. So you see that there's a part without an I and a part with an I, and that's your real part and your imaginary part. So the number a is your real part, so that's a real number. And the bi is your imaginary part. So let's see what that looks like on the next page. When we combine like terms or operate with complex numbers, you have to treat I like a variable. You can think of I as x. And that means most of the same rules apply to that. The only thing that is going to be a little bit different is that whenever we have I squared, we're going to replace that with negative 1. That's going to be the only change. So when we add complex numbers, we add the real parts together and we add the imaginary parts together. Like in example 4, our real parts, we have 12 plus negative 8. That's going to be 4. Negative 11i plus 3i. That is going to be negative 8i. And that would be your simplified expression. We added our real parts together and we added our imaginary parts together because there was a plus sign in between them. Now, when you subtract, the thing that a lot of students will forget is to distribute this negative sign to both. So I like to do that first. So 15 minus 9i. And then once I distributed that, I get negative 24, negative, so 9i, positive. Because this negative sign and that negative sign changes to a positive 9i. So now we can combine our real parts. 15 minus 24 is negative 9. And negative 9i plus 9i is 0. So we don't need to write plus 0i. We can just write 9. And that would be our answer. Now when we multiply, we're going to FOIL like we've done before. And remember, if we see I squared, we turn that to negative 1 and then continue to combine terms. So like in example 6 here, we're going to FOIL this out. We get 15 minus 3i, plus 5i minus I squared. So we're going to have 15, negative 3i plus 5i is 2i. Now, this is where, again, many students will make a mistake. We have a subtraction sign up here. That isn't changing right now. I'm just copying it down. However, I squared is -1. Oops. So I'm going to write -1. I'm just replacing this. And you can see we have minus and negative, which is going to turn to a positive 1. So it's going to be 15 plus 2i plus 1. And now we can combine 15 and 1 and get 16 plus 2i. And that would be our answer. So that I squared can trick people up because a lot of times when you already see a negative, I'll see students just say, oh, -1. But I squared is equal to -1. So for subtracting, it's minus a negative. If we are dividing complex number, we're going to multiply by the complex conjugate. I remember we talked about conjugates where the numbers are the same in the conjugate, but the sign changes. So if I have a plus bi, the complex conjugate is a minus bi. So now down here, if we want to simplify this, we multiply the top and bottom by 5 plus i. 5 plus I. And then we FOIL the top and bottom. On the top, we're going to get 15 plus 3i plus 20i plus 4i squared. All over at the bottom. Now remember, when we multiply by the conjugate, we know that shortcut. We can multiply those two terms and get 25. And we can multiply these two terms and get -i squared. So now in this next step, I'm going to combine my like terms in the numerator, and I'm going to change all of my i's to change all of my I squareds to I. So we get 15 plus 23i plus 4 times -1 over 25 minus -1. So we simplify that further. 15 plus 23i minus 4, because 4 times -1 is -4, over 25 minus -1 is 26. All right, we're almost done. 15 minus 4, combine these like terms, is 11. So 11 plus 23i over 26. That is our simplified expression. And notice that it gets rid of our imaginary number in the denominator. So these are almost about as complicated as they get. The last example here, we're going to, first, I see that, 5, 10, 15. All of those are divisible by 5. So we can divide all three by 5 and get 1 plus 2i over 3i. Now, you could do this later on in the problem, but if you recognize it now, that makes life a bit easier. Now I'm going to multiply the top and bottom by 3i. That will make the denominator not have I in it anymore. Okay, when we multiply the top, we get 3i plus 6i squared over 9i squared. And then we're going to change our i's into -1. And it will give us 3i minus 6 over 9. There's going to be two things that we're going to do. First, we need to rewrite this properly. the proper way to write complex numbers is put the real part first. So I'm going to have, this should be -9. I'm going to have -6 plus 3i over -9. The real part must go first. Now I'm going to divide. I see that these three numbers, 6, 3, and 9, those are all divisible by 3. So what I'm going to do is I'm going to divide or factor out a -3. So -3 will give us 2 minus I over -3 times 3. This just makes things look a little bit cleaner. These cancel, and we are left with 2 minus 1i over 3 as your final answer. So this is a good problem to see that you need to simplify your fractions if you need to. Now, if you look down here, I want you guys to try these ones. The clue that I want to give you for letter D right here is to distribute this negative sign goes to those two, and then this negative sign goes to these two terms. That is going to make that a lot easier. So go ahead, pause the video, and try these problems, and then once you're done, unpause it, and you can see what I got for these. All right, so here are the answers. Go ahead and check them. I showed the work for most of them, and you can see where you may have made a mistake. So this is why we spent some time multiplying by conjugates earlier, so that we can see that shortcut, and that made letter E a bit easier. You just need to remember that I squared is -1, and that is how I went from -14i squared to +14. So this is a complicated topic until you start seeing this more and get used to replacing I squared with -1. Other than that, the imaginary unit is just like x. We can't combine that. We can't do 3 plus 6i and get 9i. So we keep them separate. So thank you for watching. Make sure to like this video and subscribe.